Thank you for joining the Once Changing the World, which is India's first future tech meets sustainability podcast. And today I'm delighted and honored to have with me Reena Dayal, who's the chairperson of the board for Quantum Ecosystems and Technology Council of India. She's a technology leader and an innovation management expert who's known for her work in establishing and scaling up innovation functions within organizations and for catching new waves of technology to incubate new tech-oriented businesses. She's also the CEO and partner for Benzetton Advisors. She's on the steering committee of the IEEE Quantum Initiative, chair for the IEEE Quantum Special Interest Group in India, and on the consultative committee for quantum for the government of Telangana. She's also authored the book Innovation Magic. So, Reena, I really appreciate you taking time and being part of the podcast. So before we get into the world of the quantum computing, which is going to come, I think I would like you to pull you back because, today, we thrive with computers, classical computers, the ones in the binary space, So could you talk about classical computers, the traditional computers, how it works and how is it impacted our world before we getting onto the quantum computing?
Sure. First of all, thank you, Eddie, for inviting me. Very glad to be here and for the lovely introduction. I think that's a great way to start the discussion because when we talk about classical computing, everybody understands what we're talking about because everybody is using it, whether it is, the large supercomputers that we see today or the devices that we carry in our hands, which have become so ubiquitous. If you look at classical computing or the computing devices that we use today, they're largely based on semiconductor technology and they follow Moore's law, which is that every few months, the size of the chip becomes half and the computing capacity doubles, right? So we've seen that evolution from large mainframes, which used to fit into rooms at the beginning of the computing revolution, to the small form factor devices that we have, like the compute capacity of the smartphone that we carry in our hands today is much higher than those original mainframes, right? So I think this is how technology has progressed. All of it is at a fundamental level based on classical physics and as the underlying principle that is used for developing these devices and on semiconductor technology following Moore's law. Now, there may be different forms of differentiation in terms of how semiconductor technology has also evolved in different kinds of chips that are available today. But then largely the fundamental principles are the same and they are based on classical physics.
Right. So over the years, these entire, the compute capabilities powered by the semiconductor chips has, created great benefits for mankind, society, right from your businesses to your consumers, and right now the acceleration of technology and the convergence of all of these technologies is opening up huge paradigms. It's kind of forcing us to ask deeper questions, because I think we are getting into the world of what the Arthur C. Clarke's quote is, that sufficient advancements in technology is going to be indistinguishable from magic, and we are literally now peering into that space, because with the space of whether be it AI, whether be it the virtual reality space, whether IoT, 5G, it's really growing to a point where I think in the next few years we will be possibly building products, services and solutions which will be actually indistinguishable from magic. You have been an innovation and new tech proponent. So can you briefly talk about exponential tech stack, collective intelligence, because there's some blog that you wrote about collective intelligence, and how is it going to transform the world? And while you are at it, maybe you could also address what should enterprise do or need to know to be future ready.
I think looking at Arthur C. Clarke's quote, that's not something in the future. We have seen that happen even today. If you ask somebody from, let's say, the 1900s or even the 1920s, theoretically to visit the world that is there today, and the technology that we use today, they will find it magical and impossible to believe, right? Because you will, the way we are able to do video calls, right? This was science fiction, few decades ago. And now, telepresence and the way, and we are at the verge of a situation where with the metaverse, we will have, real holograms, and with higher speeds from a connectivity perspective, you will have a high integrity resolution, real time hologram streaming. That is theoretically possible, right? Now, we have to see how 5G and 6G plays out and how really, how soon we are able to get that technology going. But viewing something like that in real time, and in experimental setups, you can do it today, is, something like magic for people from just 3 decades ago, right? So I think it's happening all the time. The remarkable thing is that the capacity of the human mind to adapt. I think the brain that we carry is such a remarkable machine in itself, that the capacity for human beings to adapt and accept all these remarkable changes is so high that it becomes a part of life after a while. And because we gradually adapt into it, it doesn't seem like magic. But get somebody from the previous generation, and today we are living in a world of magic. Now, as we move forward, right, I think all of these technologies, as you rightly said, are converging. They're converging in the sense that they are very codependent on each other. Now, for example, when we talk about the metaverse, that's an area I understand that you're also interested in. If you just look at the metaverse and look at what it represents, look at the virtual world scenarios that we see, right, and the gaming, the gaming products that we have with the high resolution that is available. There was a time of a couple of decades ago where thinking about having these high resolution video games being played online was not possible because bandwidths were not available. So every time you have progress in the communication infrastructure, you're enabling some of the other technologies to be presented in certain formats. So live and real time interaction becomes possible. And this is particularly important to note because many of the other technologies that are associated with the real world scenarios from a virtual reality or a mixed reality perspective have been there for a little longer. And it's the communication infrastructure that enables the availability of them in a certain format. Now, here we are talking about processing power. We're talking about display fidelity. We're talking about communication for life, communication speed. And we're also talking about the entire stack being built in such a manner that is optimized for a certain scenario, let's say for gaming, online gaming. Now, each of this is an ecosystem play, right? And if we just take this example, then it's the enterprises that are in any way associated with any of the parts of this whole process have to look ahead of time and say, as technology is progressing in all of these multiple directions, what is the opportunity for me to bring to other enterprises or to consumers for B2B and B2C, that will work out in the future, because people who wait for the technology to mature and then think of applications are going to be left behind. So that's the reason why enterprises need to be really thinking about this way ahead of time. And I gave one example, but you could just look at any area. And today you're also seeing a convergence of biotechnology with the people who are biotech experts on the hardware side, because biotechnology used to be biology and hardware combination more than anything else. But now the AI scientists, the machine learning experts, all of them are getting together to create new solutions which are useful for human beings, right? And for better diagnosis, for better drug discovery, and so on. So again, we are seeing completely different fields coming together. So I think the opportunity for leveraging from collective intelligence is much higher as we go forward. Because if we want to create that person who will be an expert in all of this, it's kind of impossible given the human lifespan that we have, right? People live to a certain space, certain age, and then, we sort of, they get expertise in certain areas. So being able to work with others, being able to understand a little bit of everything, but having your own deep expertise is the mantra for success right now, I believe. So because everything requires this multidisciplinary collaboration.
Right. Reena, thank you for, addressing all of those areas which I kind of threw at you so beautifully. Yes, I think, we live in a world where I think enterprise needs to, have a little foresight and look ahead into the future and not be caught like how the entire world was caught with COVID. And yes, I think, if we and I do stress here that I think the enterprise needs to now create possibly an action team which has the capability to peer into the future, because things are growing so fast. All of these technologies which you rightfully pointed out, it's converging. Earlier, like you said, it was biotech, but now it's linking with artificial intelligence, because there's so much data which is being collected today, and data is the new oil. And if you kind of dig into the data, you could infer valuable insights which you could leverage for your business and create better products and services and be ahead of the curve. So yes, businesses need to look into the future tech and the opportunity that it presents, because the future is coming in very fast. And you mentioned the ones who don't catch the bus is going to be left behind, because I think the world is getting extremely competitive and it's scaling rapidly. Yes, I would like to point out a little bit here that with this tech, this thing, I hope that there's more conversations where all the stakeholders are involved, including the consumers and the public, so that the tech that we build is human first, because that's a conversation which I think is needs to be addressed a lot. Now we are moving from our traditional computers to the quantum computers. The traditional computers which were worked on binary codes, it was in bits. Now we go into quantum bits, qubits, where we are going to be playing with nature itself. Atoms, the source code of life. Everything, you, me, tree, star, sun, moon, the computer, everything is built out of atoms. And here we are on the journey of creating a new computing architecture. So for the people who don't know what quantum computer is, could you kind of explain quantum computers, and can you describe it in a layman's term so that everyone can understand?
Sure. Before I do that, I found something very interesting that you said, and maybe if you allow me, I'll comment on the aspect that you talked about, the involvement of the end consumers in ensuring that technology is useful for humanity, right? That is such an important point that you mentioned, and I must comment on it, especially because today we do not have enough mechanisms to actually involve this end user community, because technology is getting more and more complex and its implications are so difficult for the end consumers to understand. If you take a simple example of how privacy issues are being are addressed, there are these various websites that you go to and they ask you about cookies, right? And there's a long list. Do you think many people who are end consumers can understand what is written there? Really? No. And all of them just clicks, I agree, right? The role of the end consumer today is very, very limited. So as an industry, one of the things that I feel that we really need to do is to figure out more ways of engaging the end user community and create those end user community champions who are not just part of, some companies' a beta testing environment, right? Because then they feel affiliation to the company. But these are independent people who can actually play a role in deciding what is the right way to use the technology. And they can also give inputs to which can eventually lead to regulations, etc. It's a dream of mine. I don't know how we will accomplish that, but this is something which is really required. Now, coming to the quantum front, so let me try my best to do a layman's explanation of quantum. It is a very difficult subject. It is not intuitive, because classical computing is somewhat intuitive. Classical computing is based on classical physics. Classical physics is the physics that we see in the environment around us. And it is intuitive because we live in this environment, right? So we know when you look at Newton's law of motion, right? This is force is equal to mass into acceleration. I mean, it is intuitive to figure out that, if you apply more force to something, it will move faster, right? If you want to push a car from behind and you push it with more force, it will move forward faster. So this equation may not be understood by people who are not studying physics, but the physics behind it and the way we see the physical manifestation, and we're able to intuitively understand it. Now, quantum physics actually, quantum computing is based on quantum physics. And quantum physics is the physics of the micro, which is essentially we are talking about what happens inside the atom at very small distances. And at those distances, what is the kind of behavior that we see? Even if the topic seems tough, hold heart, it is tough for everyone, not just for you if you are listening to this. But at a very fundamental level, when you look at classical computing, we rely on information being available in bits, and bits are binary. They can have two values, either 0 or 1. And the entire, and at an implementation level, we create gates, which are, classical gates, which manipulate these bits so that you can do and or operations, more complicated operations, and use those gates and composites of those gates to do all different kinds of calculations and manipulations of these bits. And this forms the basis of the computing, right, at a very fundamental level. When we look at quantum computing, we are actually using some of the properties of particles at the quantum level. So there are two specific behaviors that are being leveraged. One is the principle of superposition. So the principle of superposition says that if there are any quantum particles at quantum distances, and we're looking at particle behavior at those distances, then unless you measure, let's say we're looking at the spin of an electron, right? And the electron could be spinning in this direction, maybe, and let's call it a state of 0. And it could be spinning in this direction, let us call it a state of 1. Now, unless every time you make a measurement, these are the two classical states that it falls back up, that you end up measuring. But while you're not measuring the electron, all the possible states are actually existing all the time. In all these directions, it could be rotating, right? So like if you imagine a surface of a sphere, then along all the edges, from the center, touching all the various aspects of the edges of the sphere is a direction that could be taken, right? And all of these exist simultaneously. This is non-intuitive. But that's what it is. And therefore, in quantum computing, we want to take advantage of features like this, and we create, we've envisaged a qubit. A qubit is an entity which has three possible states: a state of 0 or a state of 1, however we may define 0 and 1, and a state of superposition of all possible states, which collapses to either 0 or 1 when we do the measurement. So this is also a fundamental principle of quantum physics, that you only when you measure, you sort of get a particular state. Otherwise, all things are possible all the time, right? It sounds pretty weird if you just think about it, but that's what it is. At a theoretical level, from a probability perspective, that actually could mean something as bizarre as that. What is the probability of you walking through a concrete wall? It's 0, right? From a classical physics perspective. From a quantum physics perspective, assuming that you're a particle, or maybe even, at a macro level, the possibility could be, a very small value, but there is a possibility that you could walk through a wall. The probability may be very, 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 very low, right? It may be infinitesimally low, but it is non-zero, right? So this is how bizarre, it may sound. There's another very unique feature called entanglement, which we make use of. Entanglement means that if there are any two particles which are entangled in some way, so that they have a relationship where their properties are dependent on each other, then even if you move these particles any distance in the universe, any change in the state of one of these particles will reflect simultaneously with a change in the state of the other, right? With no apparent means of communication between the two, right? So this is called non-local behavior. Typically in systems, when we create a change in the environment, it impacts locally in the distance where in the proximity where it can create an impact. But we are now looking at something non-local, which means you have a particle here and another particle at a very far distance, and there is no they are in two different locales, and then you change the state of one of these and the state of the other one changes simultaneously. Now, this is a feature which is very useful for quantum communications and a lot of devices and being prepared on the quantum key distribution side, QKD, and for quantum communications. So these are some of the features. Now, what does it mean when we look at features like superposition and we look at features like entanglement? We also need to look at the fact that because of the principle of superposition, the amount of computational capacity that you have with quantum bits is much higher, exponentially higher than with bits. So for example, if you look at, let's say, n bits, right? Any n number of bits. Now, if you look at bits, then these bits can store 2 to the power n values, right, in those n bits. But if you're talking about quantum bits, they can store all possible values from 0 to 2 to the power n at the same time. This means that if you have a few thousand qubits, you are suddenly able to store and therefore process data which in numbers is higher than the number of stars in the known universe, right? So that's exponential, right? And suddenly that opens up possibilities for computation, which is not possible with the current technology to be made possible. The other difference is that classical computing is deterministic, right? It's if you do calculate a certain set of variables, you get the response, which is a fixed response, and you will always get the same response. Quantum computing is based on quantum physics, and therefore it is probabilistic in nature. You add more, layers of interpretation and calculation to give it more, to get more concrete results. But fundamentally, it is probabilistic in nature, right? So while this may seem strange, but it also, if you look at quantum behavior, there are certain algorithms in quantum which allow us to solve problems which are called a special class of problems, like the NP hard problems, for example, which are not solvable by classical computers. Some of them become solvable by quantum computers. From a layman perspective, this just means that certain computational problems do not have relevant algorithms which really solve those problems in classical computing, but they help you solve those problems better if you apply some quantum algorithms, right? So that's the promise of quantum computing. Today, we do not have a scalable quantum computer as yet. We have made rapid progress in the industry and academia. To reach a certain states, most of the quantum computers that exist today are noisy in nature. So computational capacity that we have and the algorithms that we can use is limited, but there is progress happening on a daily basis. So, once we have a scalable quantum computer, then we'll be able to probably solve all the difficult problems that are unsolvable today, most of the difficult problems that are unsolvable today.
Lovely. Reena, really appreciate you explaining quantum computers, and as basic you tried to make it, it's still, so very non-intuitive. How do you kind of understand this whole thing? Because with traditional computers, it's very simple. It's binary. It's zeros and ones and yes and no's. As soon as you enter the quantum world, everything gets fuzzy because of the dual nature of particle, the superposition, which could be zeros, it could be one, it could be one and zero at the same time, the entanglement, what is here and what could be millions of light years away. If you kind of make a change over here, that changes over there. So these things are so mind-boggling, but yet I think my listeners, I need to stress that this is the way nature functions. This is the way the world functions. Everything that's made out, the source code of everything is atoms, and that's the way the weirdness of the atoms, the probable nature of atoms are. So I think, yes, maybe we need to dig deeper, and yes, once we actually build these working quantum computers, there could be great applications because of its nature of the way things is, so tell me, somebody who's been invested in the space, before I get into QETC, what could be the probable applications of a working quantum computer? Because the low hanging fruit, it seems it's in the banking industry, the crypto industry, because those are the space which is extremely fearful of the encryption being broken, so maybe address the low hanging fruits. What would be the earlier applications of a quantum computing in working quantum computer?
Yeah, so that's a great question, because people struggle between two extremes. One is, hey, is this today's technology? Is it something that I need to only bother about 20 years in the future? And others, and on the other side, sometimes there's a hype which seems to say that you can solve all your problems today. So I think the reality is somewhere in between. Like I said, we are in the noisy intermediate scale quantum era, NISQ computers, and essentially that doesn't, however, mean that you cannot use these computers today for anything, right? So there are definitely applications. One of the strong areas for applications is quantum chemistry, because today, if you want to simulate a molecule, even a very simple molecule on a classical computer, we do not have enough uh, resources to do those kind of simulations, and especially if you want to simulate a chemical reaction. So it takes an enormous amount of computing power and space to actually do those calculations. And for even slightly complicated molecules, it's not possible. But some of these molecules can be modeled in quantum chemistry using quantum computers on very small number of qubits. And therefore, the road opens up for us to do, simulations for various kinds of interactions amongst molecules, and see what is the kind of results we can get. This is very useful in multiple areas. It could be useful for materials. It could be useful for drug discovery, drugs related on the biosciences side, on just the chemical industry, trying out different chemical reactions and stuff like that. So these can be early adopters. These are the companies that should be actually looking at real industrial uses for quantum computing in the near term, short term, and mid term, right? They don't even have to wait for the long term, and they can start using, and definitely they need to start building the capability right now. From a technology perspective, they have the least barrier. So that's how we'll put it. The second area, which is very interesting, is quantum sensors, because quantum sensing is just another way. If you're from the sensor domain, it allows use of certain very specific quantum sensors, allows your sensing to be more accurate, more focused. Let's look at, there is some discovery of a gravity sensor by one of the companies in UK, which allows you to actually understand the scenario under the ground 1 meter in depth without any excavation, etc., to see what is there, right? And this is great for infrastructure projects, for example, or for locating landmines, or various kinds of scenarios that might be there. Similarly, I don't know, for astronomy, use of sensors at the heart of this, the Webb telescope, are quantum sensors, right? There are some quantum sensors there, right? So sensors have the capacity to make everything better, understanding the weather better, and so on and so forth. So this is an area where quantum sensors are already being used. It's not day after tomorrow's technology, it is today's technology. So the third is quantum communication, which is a lot of development work that is happening worldwide. While this area will take a lot of time to really become, if you think of the quantum internet, it will take a lot of time. But there's a lot of development happening in this space. Anybody who's in the communication space knows that you're always working on day after tomorrow's technology. So, we have 5G, which is, now imminent across the world, but people are already working on 6G technology. They've been working on it for a while. and 7G conversations are starting, right? So that's how the communication industry works. So even for them, quantum communication, a focus on that right now is the right thing to do. Now, you talked about quantum security, and I want to treat that topic a little separately. Let me talk about that. I think as we move forward with the compute capacity that quantum computing enables, we are aware now that RSA 2048, which was considered unbreakable and which forms the basis of encryption of almost all kinds of data that we encrypt in different applications. And we thought that it is unbreakable because at that point, whatever compute capacity was available, it was unbreakable. It would take a few million years to break that encryption given our current compute capacities. But with a quantum computer, you can break that encryption if at the moment we cross a certain number of qubits in capacity availability, we'll be able to break that encryption in a matter of few days or few hours. Now that is debatable, it depends on the number of qubits, but given the kind of sensitive data that is there, digitized today and is used around the world, including data which is relevant for national security of nations and financial data, healthcare data, which is all related very closely to people, utility data that, the encryption that protects our utilities which are online and so on. All of that is, suspect to breakdown. So the tech industry and the tech institutes around the world have already been working on this problem statement for a while now. So the National Institute of Standard and Technology in the US had issued a certain number of, they had issued challenges to identify algorithms that will be quantum resistant so that, people can start looking at those algorithms. They finished around 4 and they announced some suitable 4 rounds. They went through 4 rounds of reviews. And, when certain algorithms are introduced into the community, which is doing this work, then there are a lot of people who try to break those algorithms, right? And prove that they will get broken by quantum. And many algorithms did get broken, right? Or were perceived to be that it will be broken, when in the post-quantum era. So finally, certain candidates have emerged, which look like the right candidates for encryption and for maybe digital signatures and so on. So those recommendations have come out in the market, and now entities around the world are now looking at those algorithms to create post-quantum cryptography solutions, which will help address the requirement for what happens when you have when you are in the quantum era. So I think this is an important problem to consider. It's important that every nation is preparing, and of course, India is also very aware about this, and work is already happening both at the industry level as well as government and various institutes to prepare for the post-quantum future, and therefore addressing the security requirements that will be required by us for that timeline. So, when we look at Y2K, when everybody had to move from to a compliant format for the 21st century, we had a clear date in mind. And of course, the problem was very simple. But when we look at quantum security, post-quantum security, we know that everybody has to transition to these algorithms, which will be secure not just today, but even when as computing capacity grows for quantum computers. We do not know when it will happen, and there are a lot of debates around the world as to whether we should be looking at the next 5 years or the next 15 years, in which case the timelines for implementation might be completely different, right? But it's important to understand here that when you have so much such important stuff at risk, whether it's 5 years or 7 years or 10 years, it doesn't really matter. And as Bill Gates has said, that he made a statement once saying that we always underestimate how much we will do we overestimate what we can do in 1 year, but we always underestimate what will happen to technology in 5 years, something like that he has said. And it is extremely true. Every time we project how a technology will evolve, we completely get it off the mark, right? And here the price that you have to pay for not being ready for quantum from a security perspective is just too high. So therefore, I think this is the right time for everybody, especially like you said, the financial sector or the healthcare sector or anywhere, the utility sector, all of them to really start looking at their action plan for moving to post-quantum security. Yeah.
Right. Yeah. So I think I would like to highlight, the same point which I mentioned earlier, that it is so important for enterprise to be ready, because, we really underestimate, the long term this thing. So yes, I think there is some crazy things happening in the space of technology, and if the enterprise needs to be future ready, it needs to take the step right now. You are the founder of Quantum Ecosystems and Technology Council of India. So can you talk about what made you start that business unit and its mission?
Yeah, sure. So I have been associated with quantum as part. I was in the corporate sector for 30 years. And in my last company, I was involved in quantum for India, right? So I was engaged in the ecosystem. So I had a fair idea of what is really happening in the ecosystem here. And I was also connected. I was already on the IEEE quantum initiative on the steering committee. And when I looked at the scenario everywhere, and I realized that there are multiple challenges in the ecosystem, and not just here in India, but elsewhere. But then I'm based out of India, right? So, and I'm thinking about my immediate ecosystem. And when I looked at that, I also realized that while the government will have its own focus to drive policy and plans for quantum in India, maybe there's a requirement for an entity which can stir the ecosystem, because the ecosystem at that point in time, I'm talking about more than a year ago, I felt it was struggling with whether we should be looking at quantum or not. And I'm pretty convinced, I've been convinced for the last several years now, that we should be very actively looking at this. For, it's the next generation technology that we will be using, and it is transformatory in nature. It will completely change the fate of nations. It will change the fate of business in terms of how businesses adopt this technology as we move forward. It may not happen immediately, it will happen gradually, but there is a need to do early investment. So I decided to formulate an entity which will be working in the ecosystem with the government, industry, academia, startups, all the various ecosystem players, and act as a catalyst and a think tank to start off with, and evolve into whatever format that we feel is the most beneficial for us to evolve into for the benefit of the ecosystem. So obviously, when you think of such an entity, one of the things that came to mind was that we decided, I spoke to a couple of other people. I think you've interviewed Dr. Arun Pati. He's also a founder director on Quantum Ecosystems Technology Council of India. And so is another person, Ramesh Ketharaju, who's working in the financial sector. So the three of us, I actually initiated the conversation, took inputs from both of them. They were very supportive, and we decided, and I brought this idea to them saying that I want to start this, and they said, yeah, let's do it, right? And that was great. We decided to set it up as a not-for-profit, so it's a Section 8 company, and its mission is to enable and accelerate the quantum ecosystem. So our focus is twofold. One is to enable and accelerate the ecosystem in India, and the second is to drive more international collaboration, because, personally, I really believe that science and technology has to rise above all the other issues and, work towards the benefit of humanity as a whole, right? And therefore, these are our two focus. And we are now little over a 1 year old organization, and been doing a lot of things in the ecosystem. Yeah.
Right. So first of all, Reena, congratulations, and it's a complete privilege to have you on the podcast and to be talking to you and to know that you have been at the forefront of driving this conversation. And I think there is a more need for women scientists, researchers, entrepreneurs to get in the field, because I think so far, I think the rock stars of the world were the musicians and the actors, but that is it's shifting. I think the rock stars are becoming these entrepreneurs and researchers and scientists who are vested in the tech space. And it's plain to see, with the likes of Elon Musk and Mark Zuckerberg, hogging all the limelight. And I hope that the Indian women, step up, such as yourself, because you are being the guiding light, of creating a conversation when it comes to a technology which you said so profoundly and rightfully is going to change the fate of the nation or fate of organizations who leverage it. And I think it needs to be drilled deep into the heads of the people or the leaders who are fronting nations and organizations, that this is the time to kind of take that step and move into quantum computing, or start understanding, leveraging, or creating a team that understands this, so that you are prepared for the future and you're future ready. So kudos to you, and thank you for taking time and being part of the podcast. Now, India. So yes, I mean it's also playing a role in the quantum technology space. Though China has been aggressively, I might say, looking at all frontier tech stack in a way which I think is leaps and bounds ahead of other nations. India has been invested somewhere around 8,000 crores and has got a 5-year plan. What are your views on India's quantum ecosystem? And for someone who's at the forefront, what would you suggest or advise on nations or students or entrepreneurial community to do to create a robust quantum system?
So you're right. I think the amount of investment and the timing of the investment has been way ahead by some of the nations like China and US, etc., and especially China. It is said, what is publicly known is that the investment is 10 billion USD. Just by far the biggest investment by any country in the area of quantum. India is, so here's one thing, right? I mean, what we are seeing right now is the second wave of quantum physics. So that while we are seeing progress in quantum as a computing, there is also progress happening on the physics side. And also, from a quantum information side, but the technology is, the area is not completely new. If you look back, there were colleges in India who were already, focusing on quantum information, right? And then there were already places. So IIIT Hyderabad had a quantum information course for quite a while. IIC Bangalore has had a focus on quantum sensors for quite some time, right? I mean, it's not yesterday's investment that we're talking about. If you look at an institute like HRI, which is based out of Allahabad, string theory and theoretical physics, quantum physics experts are all there. You've already spoken to Professor Arun Pati. He's pretty well known internationally on the quantum physics side, right? And he's a theoretical physicist in that space. And Dr. Sen, who's actually, was recognized worldwide for the contributions that he's done to string theory, right? So I think there are a lot of knowledge base and foundations that existed in India for a fair amount of time, right? And in fact, we have one of the there is a Professor Patel in IIC Bangalore who did his final thesis or his PhD under Richard Feynman, right? So we have all kinds of backgrounds and experience that already existed in India. The question was, and this is true worldwide. I think what we're seeing right now is, like I said, the second phase or the second focus that is coming suddenly, because we are at the end of Moore's law. Semiconductor technology does not have the promise any longer to give you much more higher capacity beyond a limit. You can see the end, right? You keep shifting, you said 7 nanometer will work, then 3 nanometer and 1 nanometer, but what beyond that? Now you're already at the quantum scale. So you are seeing the quantum effect. So now the technology has to be quantum focused. So now there is a much more concerted effort, and governments around the world have been investing here. If we come back to India, we've also, sort of woken up, and the 8,000 crore project that was announced, that has not yet been launched. It is on the verge of getting launched, and I know as much as you know right now, but I believe it's on the verge of getting launched. But there have been other efforts, very publicly known efforts that the government has done. For example, there was a Quest program where they, funded institutes around India for doing further research in quantum in different areas, right? And that funding was released more than 2 years ago. So there's a lot of progress that has happened in the interim period. There have been public announcements for the progress on quantum communication side, which were done by ISRO and the Raman Research Institute. So there was, we all saw those reports and those work, and the work that has been happening there is really high quality. And that is based on the photonics experience and background that India has. India has traditionally been very strong in photonics. Then, there were, the setup of labs by the Indian Army, again, a very public announcement where QNU Labs is one of the startups that is involved in. The sector, the industry sector is now getting involved. The technology sector in the industry is now getting involved. We see companies, we saw the announcement from Tata Institute of Fundamental Research about a 3-qubit quantum computer that they have made. And then, companies like TCS, Tech Mahindra, they're all investing in this space. And, Tech Mahindra had earlier announced some COE, which is, in India as well as something in Finland for quantum, right? So I think that is happening. We recently saw the announcement from Amazon Web Services and the MITI, the Ministry of Electronics. I always wonder whether to call them MITI or MITI, but whatever. They actually they are running the second cohort for startups in the quantum space, and they're and we from QETCI, we are running a hackathon, come incubation effort, which started in August and is running till November to actually start the startup ecosystem and the investor community as well, right? So I think all of these efforts are happening, and you can see progress, you can see enthusiasm. One of the things that I hold, I'm a firm believer in, is that if you look at the talent around us in India, it's a very resilient and a very adaptive talent. And time and again, I have said this and I have seen it happen. I was part of one of the first few efforts to get startups going in the drone space in India at a time where we did not even have a proper drone policy, right? And I was working, and at that point in time, there were very few people who were working on drones. I remember giving an interview like this at that time and saying that, we will see a very quick catch up. And actually it happened because of the kind of talent that we have in India, right? In some senses, Jugadu, but also, right, in the positive sense of the word. And then adapting, and, fundamentals are very strong in terms of the technical background that people acquire while they are studying in the colleges here, especially the colleges that have a good focus on academics and so on, right? So I'm very hopeful about how we will progress forward in the quantum spaces.
Reena, thank you. Really, really appreciate you taking time and being part of the podcast. My last question, and it's a little broad, and I'm going to digress a little bit. So I've been vested in the virtual reality space for the longest time, and we pushing onto the boundary. We creating photorealistic content, and even today, I think virtual reality, what it does is that it tricks the motor cortex into kind of believing the virtual the world is real, and that's proven with extremely basic, very basic virtual reality experience, such as the Ritchie's plank walk, which is which you can experience even in malls. You put on the headset, and you're in the mall, but the experiences that you're on the top of the building and there's a plank sticking out, and you walk on the plank, and your motor cortex kind of brain tricks you into believing that the virtual is real, and you scream and you fall and things like that. The reason I'm saying this is that virtual reality is still in nascent stage, but like I said, we really pushing the boundaries, and we are able to emulate the physical touch vision, and hearing, and we pushing onto the boundaries, and maybe, I'm saying that maybe we could go to a place where the virtual world could be indistinguishable from the real world. Now, Seth Lloyd is a professor of mechanical engineer and physics at MIT. He had written a book called "The Universe is a Quantum Computer." So, my first question: are we living in a simulation? Is the world simulated? That's the first question. And the second question again is David Deutsch, the father of quantum computing. He was the scientific advisor of this TV series called Devs, which came out. Alex Garland was the one who directed the TV series, and the TV series is about a company like Google who's built a quantum computing startup, and they built an algorithm, which that algorithm gives them access to the past, the present, and the future. Through the quantum computing, they can peer into the future. So my second question is, when we have a working quantum computer, possibly 1,000 or million qubits, what would the world look like?
So let me first address both of your sub questions also, so that I can then combine my hypothesis and talk about what the world looks like. I think the first thing you talked about is that the world is a quantum computer. It depends on what context you're talking about, because fundamental reality at a micro level is quantum in nature, right? So yes, then, in the physics community today, for a long time, there has been attempt to look at what happens at the macro level, which is where, Einstein's theory of general relativity and special relativity comes into the picture. And then you look at something like quantum physics and what happens at the micro level. So there has been an attempt in the physics community to reconcile those two and say that the laws of nature cannot be so separate it's like the human brain has somehow, because of our capacity and limitations, we have found these theories which do not reconcile. So for a long time, there was no reconciliation. Now, and without going too much into detail, I think what scientists are finding more and more is that the whole concept of unification may depend on the fundamental principles of gravity, and how does gravity interact, what is the role that gravity plays both at the macro level and the micro level, and maybe that can help to unify Einstein's theory of general relativity and quantum behavior at the micro level. And some of the forefront research work that is happening in this space is actually with the effort of multidisciplinary. It has somehow happened that the quantum physics people who are focused on cosmology and are looking at black holes and their behavior, and black holes are a good place where people look at when they talk about reconciliation of these two aspects of the universe, because you get through the event horizon and what happens within a black hole through extrapolation or theoretical projections of that, you're actually addressing both things that are at the micro level as well as the macro level. So today, if you see some of the research that is happening on quantum gravity, actually there are also a lot of computer scientists who are involved in the conversation, because there's something called the holographic principle that comes into the picture, right? And sometimes people run away with that concept of the holographic principle and say, yeah, the world could be a hologram. Now, when we talk about the holographic principle from a physics level, it's not exactly about the world being a simulation. It is more about where does information reside in the universe? And does it reside at the same place where the entity exists, or does it reside elsewhere, and what is the correlation? So these are early stages of research. I feel that when we say that the world is a simulation, we actually misinterpret some of this and try, because we don't fully understand that part of physics completely either. And therefore, this extrapolation of that this world could be a simulation. I mean, theoretically, anything is possible as long as we don't have the fundamental theory of how the universe works. You can, just place your bet on anything. But if you look at whatever physics has been built through the past, I don't think we have enough evidence to say that this world is a simulation. I may be wrong, but that's my personal opinion. I don't think it's a simulation. The second thing is that once we have a quantum computer, the mind boggles to imagine if we have a fully scalable quantum computer, what do you need to simulate the universe, right? Think about it. We know nothing about the universe. We know like a very small percentage of our knowledge is so limited in terms of what this universe is, what are the various laws, what are the limitations of the human mind. So we can only perceive what we can perceive. We don't even know if we understand the whole thing because we cannot even comprehend the whole thing, right? So we can be living in this bubble and saying, hey, we got it right because we can't even perceive through our senses what all is out there. In that scenario, trying to even think about just because you get access to a quantum computer of superior capability will be able to do something like simulate the conditions of the universe to be able to look at the past, imagine, compare it with the current, and then be able to project this future with, great accuracy. Again, I think that's a very, very tall order. I don't think it's possible to fully be able to predict the future. Staying in the current. According to Einstein's theory of special relativity, you could travel into the future, but then you have no way to come back to the past. If you have a spaceship that allows you to move at the speed of light or at a certain speed greater than light, and you time yourself correctly, you want to go there, out there somewhere, come back to Earth, you could come back several million years into the future, but there's no way to go back, right? I mean, as per the laws that we understand them today. So it's very, I think this is all very good stuff for science fiction. Maybe somebody should write some more stories for the enjoyment of general public. But from a science perspective, I don't know if we can completely predict the future anytime soon or later. That's what I would say.
Right. Thank you, Reena. Really, really appreciate you taking time, being part of the podcast, sharing your insight and foresight. Wish you and your team the very best with the Quantum Ecosystem and Technology Council of India. You I believe, are one of the leaders in the space here in India, who's been the guiding light and taking the field forward. I hope that more people join you, share your enthusiasm, and make quantum ecosystem here in India robust, so that everybody understands, and then we transition into it seamlessly, so that everybody can leverage it. So thank you once again for taking time and being part of the podcast. And to my listeners, if you like what you see and hear, then please press the subscribe button. And until next time, see you guys. Bye bye. Thank you.
Thank you for having me. Yeah, it was a very nice discussion.